All right, welcome everybody. Good morning. I'm Sam Burden, Assistant Professor in Electrical and Computer Engineering, and it's my pleasure to introduce our speaker today. This is Dr. Monroe Kennedy III. He's a freshly minted PhD, submitted his dissertation, defended in mid-February, February 15th, and then submitted his dissertation last Friday. And then next Monday, he'll start his research engineer position at MIT Lincoln Labs. Monroe comes to us, he did his bachelor's degree at University of Maryland, Baltimore County, where he was a recipient of the prestigious Meyerhoff Scholarship. He was a member of the 20th cohort of that program. He did his doctoral work at the University of Pennsylvania under the guidance of Vijay Kumar and Kostas Danielidis in the world-renowned GRASP lab and in mechanical engineering and applied mechanics. Really excited to be introducing Monroe today because he's a real rarity. He's a full-stack roboticist whose work, in my opinion, combines the best aspects of both classical modeling and control techniques with more modern algorithms for machine learning and perception. So let's give Monroe a warm welcome.
Thank you very much for having me. So today we're going to talk about modeling and control for robotic assistants. So let's go here. All right. So the outline today is we're going to really focus on wet lab assistance. Specifically, we're going to look at two cases, one for experiment preparation and the other cooperative transport in cluttered environments. So if you really think about the history of robotics, I think there are three A's that have been guiding us. In the 80s and 90s, we were big on automation. In the 2000s, we saw the emergence of autonomy. And then more recently, we see the emergence of augmentation. So automation, you had these robots that were able to work inside of these environments and do very repetitive tasks, which was able to save a lot of time. And then we have autonomy where these robots are now capable of observing their environment and understanding their place in it. But now we're moving to a place where we want these robots to work really closely alongside people and be able to do things that are repetitive, have that autonomy, and then be able to account for these unstructured environments and the people that are in them. So if you think about assistive robotics, some things that drive us wanting to do this are increasing safety as well as convenience. So there are many examples that you can see here, and if we can address just a few of these, I think we can make the world a better place. So what we might also find is that some of these abilities might actually be interdependent on different scenarios you can imagine wanting the robot to do. So you could have a wet lab assistant and there are things that you might want to do like pouring, but maybe inside of a wet lab you also need to carry. But if you're in a home as well, you may be able to help someone carry something in a home as well. So some of these tasks translate very well between different environments that you can imagine having these robots in. So today I'm going to focus on wet lab robotic assistant. This was motivated by a pharmaceutical company in Pennsylvania, and they approached us and told us some cool things they'd like the robot to do. And in my thesis, I was able to address a few of these tasks. So some of the things that they were interested in was precision pouring for experiment preparation, cooperative transport for large and heavy objects, replacing and restocking equipment, experiment cleanup, as well as maintaining cultures while scientists are away. Did not do all of these in 6 years. I was able to focus on these two, precision pouring and cooperative transport. So let's start with precision pouring. So how can you complete first a complex task? So if I give you this process model where X here is your state, and then you have some measurable output Z and some control inputs U, the task becomes how can you actually observe your environment to have some notion of understanding of what the state of your system actually is. And then whatever your objective is, you need to be able to describe it in terms of a final state that you want to reach. And then once you understand what that is, then you need to design a controller that allows you to reach that final desired state. So if we think about precision pouring, where we put the condition that as you pour from these containers, here the full container to the empty container, you have a single attempt to pour precisely from this container the precise amount of fluid. Can you do it? How can you do it? And one really hard part is how do you actually model and plan for these very complex tasks. So some of the goals in precision pouring are pouring using containers that are found in the lab, being able to pour precisely, quickly, and then we want to be able to minimize the tool change requirements. So can I manipulate containers that exist already in the lab? And if there are new ones that I've never seen before, how can I accommodate that using just the grippers that I would already have in case I want to transition to another type of task? So why this is advantageous to the wet lab researcher, this can save a lot of time when it comes to doing rapid experiments and that don't justify use of big machines to do the same. And if you're doing this, if you can handle some of the more volatile liquids, you can actually increase safety for the scientists as well. So to show why this is hard, we had this great video where this toddler is going to pour some fluid, and our robots are a lot like toddlers. So let's see how she's able to do.
Whoa, was a decent.
So really looking at the things that she found challenging, we saw that spillage was an issue. We saw that perceiving fluid in the container was an issue. And then she had issue attenuating the rotation based on the fluid flow. And then she had trouble anticipating the time delay during pour for the fluid that was exiting the container, the pouring container. And so she was very shocked. Our robots get shocked too, but when they get shocked, we can't use them anymore. So we want to avoid that. So some additional challenges are container perception, possibly perceiving fluids that are clear or transparent. And then how do we actually model these flow dynamics? So I'm going to present two scenarios to you. The first, we're going to assume that we have analytical models for both the pouring and the receiving container. And in the second, we're going to assume that we don't have an analytical model for the pouring container, but we're going to try and estimate the parameters needed in order to control and pour well. So in the first scenario, we're only going to observe the volume inside of the receiver. And in the second scenario, we're going to observe the geometry from a single scan of the pouring container. And then we're going to be able to observe the volume inside of the receiver as we pour. So first, with the first case, we assume that all the geometries of the containers are known. Analytical representations exist for all of them. No spillage occurs, the volume in the receiver is observable, and the time delay for the small container is negligible. So our problem is, what is the control input that allows us to pour the desired volume? So if we look at some related work, this is actually some amazing work done here, and this is just a small snapshot. So Fox has been my guide as I look toward what has really been done in this work. So here's an example where they actually are looking at use cases just in containers that would exist in the environment. You want to pour these kind of fluids, but they weren't focused on precision. They were focused on pouring a relatively general amount of how much fluid you wanted to do. And in this work, they had 11 volume classifications. There was later work where they looked down from the top and you can actually see the fluid inside, and they were able to get within 30 milliliters of their target. And so while the objective is a little bit different, this isn't the use case for the pharmaceutical industry, this was a really good first step in this direction. And then you have some work here where they're able to pour from the container multiple times, and they're able to reach their target volume, but they have to have demonstration. So if I give you a brand new container and I say you only have a single attempt, you don't have time to pour multiple times chemical X. You have to be able to do correctly in a single attempt. And then you could say, well, why not just have a very specialized system? So here you have this Monroe robot lab assistant that has pipettes. It's able to pipette and do all of the exact experimentation you want. This is a viable option. However, if you want this robot to be able to do very diverse set of tasks and transition quickly, then you don't want it to be as specialized, and you want it to also work safely around human counterparts. So we're trying to find that middle ground solution that works well and robustly in these unstructured environments. So first, we started off with our known containers. So we had a camera, we had a container geometry that we knew, and then what we did was we used Bernoulli's law. So we assumed that the fluid was Newtonian. We knew the properties of the fluid, again, in our assumptions. And so then we could just have this simple flow rate model. So here, the change in the volume in the receiver, V beta, is equal to the negative of the change in the volume inside of the pourer. And you could think of the volumes above and below the surface of the pouring surface. And so using this, you can actually have expressions, analytical expressions for these volumes if you assume that the height of the fluid above the pouring lip is small, relatively small. And then you can actually use these to expand your flow rate model. And this is very simple. So you have the omega, which is your input, the partial with respect to the area, where here you see this A, as well as the volume below the surface, and then the change of volume above equals the change in the volume inside of the receiver. So Bernoulli comes into play when you want to think about the fluid exiting the container here. So if I think of this abstractly, you have some area, you have some lip function which describes the edge of the pouring container and the height of the fluid. You can look at this flow rate, and if you use Bernoulli's principle, you have this expression for how you expect the flow rate out of the entrance of the container. So what's really nice is if you can prescribe the geometry of the container, here we use a square with these parameter descriptions, you can actually have an expression for each one of these parameters. So here the lip function is constant, and then your flow rate and its derivative are functions of the lip length itself, the height of the fluid above the pouring edge, and then if we want to look at the volume above the pouring lip and its derivative, and the area and its derivative, it's also a function of the geometry of the container. So here the height, the length of the container, as well as the width. So if we differentiate this flow rate model again, we can actually get a nice dynamical equation. So here we have, in terms of all the parameters that I just described, I have this second order derivative of my height inside of the receiving container, h beta, as a function of all the parameters for the geometry of the container that I'm pouring from, as well as my input here, omega. So if I think of my state space as the height, its derivative, as well as the angle at which I hold my container, then I can represent this in a very nice model form, which you're probably used to. So x dot equals f of x plus g of x u. And all I really care about is the height inside of the receiver. So I'm going to have an output function that maps from my states to the first height and its derivative. So if my objective is to pour quickly, right, but I want to make sure that a lot of sloshing doesn't occur, there's some really nice work that says if I have a sigmoidal trajectory, I can minimize the jerk and the sloshing inside. So I'll prescribe a trajectory, the height z output desired, that's a sigmoid trajectory, and I want to track this error as a function of time. So what's really nice is if I have, this is my output function g, I can show that if this is full rank and involutive, then I can actually do feedback linearization. And the conditions for that is the fact that the angle is, the height inside of the receiver is always changing, and the angle is not at the limits. And that's what these two states describe. So now, what's our objective? So we want to actually minimize this error with time. So here you have Q, it's a positive semi-definite matrix. If you wanted to select, it doesn't have to be isotropic, but it's up to you, subject to the system dynamics. So the proposed hybrid controller is of this form. So if I'm outside of my joint limits, I don't move at all. If flow is not initiated, so x2 equals 0, then I initiate flow. And then once flow begins, I can use this feedback linearization in this state with my control objective S, which gives me a feed-forward term, and then PD control on that error for the height inside the receiver. So what's really nice is that this simple hybrid controller is able to capture all the states that you actually see and observe when you're actually performing this task. So if flow isn't initiated, then you can't use the notion of feedback linearization. So this state pushes you into this hybrid state by initiating that flow. If you overshoot your target, you'll back up, right, or you'll stop, right? And then to reinitiate, if your error is, again, positive, you can then use this to reinitiate the flow. So that's the nice aspect of this hybrid controller. And so when you're in this state, right, you can show that you have feedback linearization with the following conditions on your gains. So the output from this is to say, okay, if I want to pour this container, I can pour at different volumes, and then just to show robustness, you can pour this at 100 milliliter target for 100 trials and 10-second trajectories. And then initially we used just looking at blue fluid, so we used just vision and compared it with a scale that was very low speed. And one issue that we had initially was you could see the back of the fluid, and so you had some disparity with where you were detecting the fluid, and so that causes this dip that you see here, which we adjust later in an algorithm that I'll show you in a moment. So this is just a video demonstrating how this works. So again, the fluid is colored blue, so it was really easy to use online background subtraction. And then the MV Blue Fox camera is detecting that. The red line is the target line. The green line is a filter line to make sure that we weren't detecting fluid that was falling in and having our estimate rise too quickly. We used k-means clustering to detect under the filter line which points belong to fluid entering the container and which were the fluid rising up. And we're able to do a really decent job and pour very aggressively. So to improve on our estimation technique, we then combined a scale, as you would imagine, it was a good idea, as well as vision. And vision served another purpose in our final implementation that allowed us to even detect where the pouring container was so that we would move to the right place when we initiated pour. And so using these, we were able to combine vision and weight. And what's really nice is for the vision, we were able to detect all types of fluids from different colors as well as transparencies. And here you see this network based on this architecture able to detect water pixels of these different types. And so this was able to really work well. So vision had more variance, but because it moves a lot faster, it really helped us with our estimate with our Kalman filter. So we've looked at the case where we know both container geometries, but what happens when you don't know one of the container geometries? So looking at this case, we assume again that we can scan the geometry of the pouring container once, but we can observe online the receiving container's volume. So this is the one change in our assumptions, that we assume that the geometry of the pouring container is observable, but an analytical representation does not exist. So again, we have a similar control objective. What do we need to control? How do we need to control in order to reach our desired volume? So this you could imagine as being a full state machine for our system, but we're going to focus on scanning the container geometry and performing that precise pour. So again, revisiting a similar dynamical equation, we're assuming again we have our Newtonian fluid, and we can use Bernoulli's principle. So here's our flow rate. So now we have the time, the volume in the receiver is equal to whatever current time of exiting the container plus the time it takes to fall. Now that's relatively negligible. It's about 0.11 seconds for the relative heights that we were holding the container geometry. But if I actually split this up, I can think of the fluid below the pouring lip as being steady state. If I stop rotating and I held it still, this is how much fluid would remain inside of that container. And the red is transient, so we're going to define it in that way. So this can be difficult to model when you have different container geometries. So we're going to do a little trick, and we're going to add this transient time to this term TD, which is our ultimate time delay before what you see in the pouring is realized in the receiving container. And so here we have this term here, this dv d theta, and this is going to become important in a moment, and then our control input, which is the omega, or rotation of the pouring container. So this time delay is a function of the container geometry, the angle in which you pour, you're holding it, as well as the control input history at the last moment. So again, we're going to define our error in a similar way. We're going to have a desired trajectory we want to track, the volume inside of the receiver, and this is what we want to attenuate. So by minimizing this cost objective function, similar to the previous version, we can hope to achieve and minimize the error and track the volume we want inside of our receiver. Key is that time delay is really important. There's a time delay in our plan. If we rotate and we stop, right, because we think we've achieved our thing, whatever is above the transient will actually go in and we'll always overshoot our goal. So it becomes extremely important that we be able to have a good model for the container and estimate what that time delay is so that we control the future error and accommodate that time delay in our plant. So if I think about this volume profile, this is the key breakthrough here. For the pouring container, at every angle that I hold this, there's a maximum amount of fluid that could be in that container at that particular angle. And if I look at the receiving container, I can actually build these volume curves for different angles that I'm rotating it at. And if they start off with zero fluid inside of the receiver, then the derivatives would be equal and opposite for the pouring and receiving containers, these volume profiles. So what's also important is that we also establish this notion of distance between containers. So in this work, I'll talk about symmetric containers that we tested, but this could be extended to non-symmetric geometries. And if I have this function, which is a radial function, which describes the radius from 0 to however tall the container is, I can compare by having this term s, which goes from 0 to 1, which parameterizes the height of this container. I can then integrate and say the difference between these two is the distance between these containers. So I only need to look at one edge for symmetric containers and compare that radial height to say how different these two containers are if they're open containers. So the similarity assertion says, as the two geometries approach each other, I expect the volume profile to be the same. So the way we did this for real containers is we scan the geometry. So here we use a time of flight sensor to extract a point cloud. We use Ransack, get the table, Ransack to get some cylinders fitting up, and then we use a Gaussian process to fit the edge of our container. And now we have this notion of this radial height function for a real container. And so what we used is a fluid modeling software. So here, NVIDIA Flex, it's really awesome. And we're able to actually pour these fluids for different container geometries. And then if the container we're looking at is similar to ones that we've simulated, we can find the top 10 closest and use a mixture probability to see how close we expect its behavior to be to the simulated containers that we poured from. So this is the full control diagram. I have my control input, but the things that I don't know are the volume profile as well as the time delay. These are things that I need to estimate in order to do a good job and pour precisely. And I need to control on that future error, by the way, because of the time delay. So what I'm going to do is present the method, and this is really the crux here, is we combined online system identification with model priors in order to do a really good job in both cases. So if I didn't know anything about any simulated containers, I could begin to pour this, and as I began to see this volume profile, I could fit this function, and it will give me some expectation on a time delay on how I expect the system to behave. But if I give you a weird container, this time delay, if it's pretty large, this may not be a really good fit, and you could have a lot of error in your model. If I give you a model prior, if you poured this container before, for instance, you know how it's going to behave on a future time, and you can control for that in your plant. But now, if you have a new container, you can basically assert, if it's similar, I can use this notion of the model priors, and if it's very far, I can use this notion of system identification, and maybe I can blend these in some way. So the system identification point here, we're just using a time series polynomial fit, and what we want to do is fit the polynomial that minimizes this objective. So this first term is the residual. So for points that I've already poured, I've seen some of the volume, I want to minimize and fit that part. Right? And then I have a regulator to make sure that I don't diverge, and then I want to respect the physics that inside of the receiver, the volume should always be increasing. And then for the learning side, if I think that my manifold is relatively low curvature, I can use a Bayesian approach. So a Gaussian process here is a radial basis function Gaussian fit. So here you have the variance, you have the exponential function, the difference between two angles for a container that you're testing versus a training container, and the distance between them, L. And then this is just white noise added on to that. So what's really interesting here is you want to assess the quality of how well you expect your model priors to behave. So to do that, what we did was we incorporated the edge error, which is the distance between containers, into this variance function. So if you're very far from your training set, this variance gets very large, you can converge to your mean. If it's very close, then this variance is small, and you can converge to the examples that you've had. So with these, you can construct some variance matrices. You can have the information matrix, which this is for the training, and this allows you to train in one step for those of you who've done the Gaussian process. And then you have your mixture probability, which I talked about before, for the top 10 containers, geometries that are closest to you. And this allows you to estimate for their volume profiles how you expect your volume to behave. But if you're very far from your training set, right, then this variance becomes very large and you converge to your mean. Here, the mean is 0, so your function becomes flat. And that's meaningless for a container that you're pouring from. So how can we actually combine these? To do that, we use semi-parametric modeling. So if you're pouring your container and you're doing a really bad job, you're very far from all your training set, then your variance will increase, as I just mentioned, and that's encoded into your variance functions, and you converge to your mean, which is the system identification. But if you're doing really well, you can converge to your model prior. So in this one shot, you can see how if you can use a Gaussian process and your manifold is low curvature, you actually are able to do a really good job and determine whether you need to use system identification, that model-based knowledge of the model, versus the trained model priors that you have. And so for the time delay function, again, we had these container associations, how close we were to the geometries that we were interested in. If we assert that the following space of geometry, angle, and angular velocity is continuous, then what we did was for these simulated containers, we sampled different geometries, different angles that you stopped at, and different pouring rates, and built a manifold representation for how we expected the time delay to be, where this convolutional layer basically extracts the points along the radial function, and because it's convolutional, you have the notion of the association along the edge of this container. So you have this notion of abstracting a property of the edge of this container profile. And doing this, we're able to have an estimate of the time delay as well, which is fairly hard to compute otherwise. So again, our control strategy is very similar to the one we did before. So here we have our hybrid guard and resets. And then this looks very similar to what we saw before. So here I have, again, my feedback linearization. I have my proportional gain on my error. But the key is I'm controlling on an error at a future time TD. So that's the magic. And so again, if you have this initiating flow, you can initiate your flow. And when you're in this state, then you can leverage, again, this feedback linearization. And so for the stability of the controller, you want to minimize this error with time. You can expand the error in terms of your controller input. And then if you choose this Lyapunov function, for example, the conditions for stability are as follows. So if you are pouring your desired trajectory stopped at a particular height, let's say you reached your target, then you can show that if you're in that first hybrid state, then this is your condition. So for positive Kp gain, you're going to attenuate to your desired height. But if it's changing, then you have that escape velocity problem. And that can be accommodated by either increasing your Kp gain, or in your trajectory design, if your error gets too large, you can pause and let yourself catch up. But ultimately, you will be able to converge to your desired volume. So this is the method of trajectory generation. So we use this, again, you have the sigmoid property by using this trapezoidal fit, where we look at the residual for the parametric version, and based on that residual, we bound the maximum velocity that you can pour at. So if you're doing a poor job, pour slower. If you're doing a good job, pour faster. But because we kept this constant for different containers, in a minute I'll show you, this for very large containers, this can be a negative effect. You may even want to lower this if you get very large containers. You want to minimize that maximum velocity because there's more variance because your container is just larger for the volume that you pass through. So this is showing the data for this particular container. So these are violin plots. So it's a box plot inside the median, your quartiles, your extremum, and then this shows the distribution of the data. Here's the number of data that you used to generate this. So 30 trials using the parametric alone. So this is just the system identification. This is just the model prior alone, and then this is the combination of the two. This is the error pouring 100 milliliters and the time it took to pour it, and then 150 and 200 milliliters. Here again, the number of trials, and these correlate. So what's interesting is if I pour different container geometries, and these are the final errors in milliliters, so this is about 2 milliliters, this is performing quite well, and sometimes in different scenarios, the containers that you had as model priors allow you to actually do a really decent job compared to what system identification may be able to do, and you really don't know which, based on what you trained, if you don't know what containers you're actually going to be testing. But what also is really nice is that in general, the semi-parametric method is usually interpolated between these two. So it can really take the best of both worlds. And that's demonstrated really in this next case. So here I have a container geometry, and it's very poorly fit to these model priors. So here, the semi-parametric method approaches what the parametric method is able to do. So you go, okay, well, why is that important? Well, if you actually want to think about a deployable system, you're never going to touch this again. You want to be able to leverage the best in both worlds. If you have really good model priors, you can pour quicker, and that saves your scientist time. But if you don't have really good model priors, you need to be able to accommodate that and operate well in that scenario. And this allows you to take the best of both worlds if you decide that. But you could do whatever you like. So here's another way to show this same data. So here are the model, the containers that generated it. This is the prior volume curves, and then this is the final estimate. So because it was so close for these different times, the profile actually didn't have to go that far, and it did a decent estimate for the angle versus volume. So for 13 different containers, I talked about the fact that the maximum velocity was capped, and that was engineered just to be that volume. So for larger heights, container heights, you see this larger mean invariance associated with the final error. It's still not horrible, but more than what you have with a smaller container. So one way to accommodate this, again, is to slow down your pour, and then these are just fit with Gaussian process functions with radial basis function with these parameters to show you just that linear fit and uptrend and the variance associated with that. This is the same data showing the error versus time. And so the closest one who's done anything similar, in fact, is the work done here for pouring into opaque containers. So different objective, and the time that it took to pour that was between 30 and 35 seconds. So we're similar, 25 to 35 seconds. We're similar in that range as that work, but with the goal being different to pour precisely, we think we're able to do quite well. So this video shows the entire pipeline. So here we're going to first scan this container geometry, and we're going to extract the profile of the container. And then the next shot you see here is we're fitting that profile for the container. And then for the simulated containers, this is pouring done in NVIDIA Flex. So the properties of the pour were matched empirically to that of the fluid, known fluid. So if you wanted to extend this to other fluids, you could empirically match those parameters, and then you could do this for whatever fluid you want, but that's labor intensive, and there are maybe other methods that might be better to do that. So here again, we have our method of detecting the water pixels. Again, we have the filter line. Our red line is the target line. Objective was 100 milliliters, and this is sped up times 4. And now you have this really nice interface that allows you to see as you pour this volume. So this entire pipeline we took to Germany last April and demonstrated there in the KUKA Innovation Award. One second. And so here is their spotlight video. So this shows the entire pipeline you can imagine deploying. So you tell it how much volume and from which container. It scans a very dynamic setup, finds the container that you're interested in, goes down, grasps the container you want, transports it to the pour location. Now the camera serves the additional service of finding the pouring container so that you know where to begin pouring. But after that, you assume that it's static. And then you pour into that container. Then you can use a combination of vision and the scale, as I mentioned, to detect that fluid on side, and then you can replace the container. So doing this, you can imagine, being able to perform this mixology and pour the container, pour the desired volume from different containers. So now we looked at both of these cases. The takeaway is it's really good if you have a good understanding of the underlying physics of your problem, because that can really help you to perform very well in scenarios where training and the example data you have might break down. But if you have this data, you want to be able to seamlessly transition and leverage the best of both worlds when possible. And then it's good to have a controller that can accommodate all the different modes of your system and feeds on the accurate model that you're able to generate. So now I'm going to quickly transition to cooperative transport. So here, the idea is to carry this load with the human counterpart. So similarly, you want to go from A to B, and you have your states. So maybe you can perceive the human, you can perceive your environment. You need to model the expected human motion as well as the combined system motion, and then you need to determine what the robot inputs should be. So if we watch these movers carry this piano, they're able to do so without hardly talking at all and hardly hitting anything. Except for that. They didn't do a good job there. Glad it wasn't my piano. But you see how well humans are able to do this. They understood how to navigate this cluttered environment together, and they used some sort of implicit cues to do this. So how can we help robots to do the same thing? So what if the robot knows the intended goal of the human, of the system, and you assume that the collaborator doesn't want to collide with obstacles and that you also want to conserve energy, which means minimizing the forces and possibly your path to reach a target. So how can robots optimally, described in this way, transport loads with collaborators when explicit communication is not viable? So to do this, we'll examine first the notion of optimal transport as I just described. You want to go from A to B, avoid collisions, and conserve energy, which means motion and forces. So part of our work was to say, okay, well, if we know where the final goal is, can we plan collision-free trajectories that will allow us to reach there? And so to do that, if you really want to gear this around the notion of a path that you're trying to traverse, if you have a seed path generated from like RRT Connect that's really quick, you can then build convex corridors that overlap and then plan optimal trajectories that optimize some objectives, such as distance, through these corridors that you generated. And that can allow you to do the path that you want. So we do this on a real robot, but I will fast forward for now. So comparing this to similar methods, if I give you a cluttered environment like this and you want to transverse from point A to point B, if you look at similar methods that do this, like Iris, do a really good job of what they set out to do, which is decompose the free space. But the computation is very expensive. So you have to expand these ellipsoids inside of these convex regions, and you have to do this for everywhere so that you know where's good to actually traverse. But if you use our method, the computation is a lot less because it's structured with the intent of actually finding the convex around a seed path that you generate. So for that mechanism, it's very advantageous. So then if you want to conserve forces, you can really think about the interaction forces. So these are the forces that don't contribute to motion. So they produce stress on the object that you're carrying. So if you have this traditional equation, so here I have my wrench, my force, sum of forces, sum of moments, R is a positional vector. I can represent this grasp map G. And then the interaction forces are those that are pairwise between different robots. So Fi, Fj, robot I, robot J, and then this is the unit vector of the cord that connects them, and this is the interaction forces that either squeeze or extend the object, connecting those. So there's a lot of work that came along and said, well, if you can actually get them all to reach consensus on this solution vector, which is relatively low dimensional, then you can actually allow everyone to minimize these interaction forces and conserve energy. So our first work was to say, well, this is great. So what if we had the robots that were able to communicate with each other? If they could reach consensus on the solution vector, they could minimize those interaction forces if this was robots carrying things with robots. So to do this, if you know where your goal is and you planned a collision-free trajectory like we did in our previous work, then you know what wrench you need to be applying at this particular time. But you don't know where all the other agents are, but you're able to communicate with those that are within your communication radius. So if you can reach consensus on that solution vector with your neighbors, then once you've reached that consensus, you all can agree upon your control objective, where here you want to attenuate along the path which describes the wrench, how your force should be changing in order to reach your target. And your input is the change in that force, or the change in that solution vector needed to achieve that target and move along that trajectory. So now, what if you have an unknown goal? The robot doesn't know where the human wants to go. So this is particularly important when you want to work with humans and not robots with robots. How can you still do the similar thing and minimize these interaction forces? So similar work that's been done, going way back to 1999, you can imagine one really good way to do this is to actually leverage compliance. So if you can pull along, the robot can be like, okay, you applied a stress, I'm going to move along with you to mitigate that stress. Right? So this is a really good way to send that signal to the robot. However, you can imagine that you can actually spend a lot of energy pushing certain robots. So even if they're very sensitive, you have to apply some energy, and if you move faster, then the inertial effects take over. So it's really good if you could do more. So what we propose is we want to adapt to the system dynamics, manage the load distributions, and then planning in unstructured environments, we want to find the most likely path the human intends. And if we can do that, we can approach a centralized system where every agent knows where to go and there are no internal stresses because everyone knows where they should go. So if we think about what it's possible to actually measure, you could think about possibly observing the human's head, observing the wrench that they apply, looking at their feet, and then maybe the twist or the velocity of the load that's being carried, and maybe you can examine the surrounding obstacles here being a top-down view. And the physics intuition behind this is that the position at some future time, t, is a function of these parameters. And if you think about perhaps the wrench, maybe it's indicative somehow of the acceleration that if you integrated it on a small time horizon, you could estimate what the pose is. Likewise, for the head and the step, maybe they're indicative of either acceleration or intended velocity if you integrate them. So to do this, we realized that the way in which you combine these can be fairly complex. If you're in a hallway and you look down the hallway, perhaps the wrench is really important, but if I look toward a wall, if I assume I don't want to collide, that's not useful. But in an open space, I could look in a particular direction, and I might apply a force there. So even these things may be coupled, and they may even be dependent on the surrounding environment in order to achieve your objective. So if you think about the things that are important, what are the measurable quantities? Again, you could possibly look at the human's head orientation, and I have open source software that allows me to extract that vector for the head, extract a vector for the position of the person so that I can calculate the step. I can measure the wrench, and as well as the twist of the system, and I can extract the local map of obstacles around me. To do this, we built a sensor, and we realized that the best way to understand this would actually be to look at the way humans do these sort of things together. So here I have motion capture that allows me to use a motion capture system to get my odometry. I can get the forces that I'm applying. I can watch my feet. I can use a Kinect to watch my face. And then I have a student that works with me, Malachi Hopkins, and his task this summer was to look at me and try to anticipate where I want to go without using any explicit communication. Then we wanted to transfer that to the robot. So we built a map of our environment using the fetch, and then he and I carried this load around several maps, collecting this data. While he was doing this, all of the measurable quantities that I mentioned were obtained. And we did this over 6 different maps. We walked around for about 2 minutes collecting all of this data. And so at a high level, this is the objective that we had. So using all of this input, if I assume a Markov process, I only need to look at all of these quantities at one instant. Can I predict on a small time horizon, small being under 2 seconds, what the expected pose would actually be? So here I have a convolutional network that takes in the local map, fully connected networks that have this association between the head and the step, because I think they're associated in the position. And then all of these are combining with the wrench and the twist to have an estimate on the final pose. So I adapt here the nomenclature from my inspiration, Dieter Fox. So this is a convolutional network. So this is the number of layers and the convolutional channels and the number of kernels, the kernel size. And then you have a reshaped, fully connected, and this is just giving you the full details here, where these terms for the head and step, they're normalized, the vectors are normalized in the plane, SE2 plane, and then they're scaled by the velocity vector, and they're only used if they're in the same half space as the velocity vector. So they have the same association of expected position, and then I can actually project this forward to have an estimate of my pose at some time horizon. So the entire pipeline would be you estimate the goal pose, you plan a collision-free trajectory, and then you control along that trajectory. So showing the training on a holdout set, which was 15% of the data, and here you have different look-ahead times, so 2 seconds, 1.5, 1 second, and 1.5 seconds, and half a second. What you see is the error is actually lower for smaller times, which helps to fortify that hypothesis that the Markov process might be a good metric. But if you have longer time horizons, this is going to be poor. And if you think asymptotically, if I want to predict, 5 minutes away, I have no idea from just looking at this instant what I'm going to be in 5 minutes. But on a very short time horizon, maybe this will be, in fact, helpful. So likewise, the first one was for the position. This is for the orientation for the holdout set of 15%. So here are the data sizes for each one of the time horizons that I'm looking at. And if you look at this is relatively small amounts of data. And we're able to do really well. And the idea here is we believe that it's because we designed that neural net with that intuition of the physics that we're able to do quite well with such low amounts of data. So the trade-off here is if you want to have more computational freedom to do other things like plan your path because you're doing this online, you want to have a longer look-ahead time. But you're going to be more accurate if you're able to do shorter look-ahead time. So this is the trade-off we're going to have to play with. And moving forward, I'm going to show you the results for 1.5 seconds. So comparing that for each of these times for just an integration of velocity, you can see the trade-off here for position in centimeters for these different look-ahead times, and then the angle in degrees. And so in both of these cases, you can see that initially they're very close, but for the longer look-ahead times, the neural network actually outperforms this, and is showing that this data was in fact useful. So in the video I'm about to show you, this is the data for us walking around. The red is the pose of the object that we're carrying. This is the local map where we're always going to be in the center of the map. This is in Arbis, so this is a bird's eye view. So it has a little bit of the refraction situation there where you have the fisheye lens. And so sometimes it may look like we collide, but it's just a property of that fisheye lens. We're always in the center here and we don't collide. And then the purple is the predicted pose. The red is the actual pose of the system. Blue dot is where my feet were. This frame that you see here was the carried object frames. And then these other vectors are like the step, the head as well. But what we really want to draw attention to is just the purple predicting on that 1.5 second horizon what the red was going to do. So here we're standing still, we're getting ready to take off, and then we begin walking. And so then the purple begins to predict on a 1.5 second horizon before us where it expects us to go. So it's not perfect, and this isn't an end-to-end solution, but it does decently well. And if you can actually minimize that error over time, then you can actually hope to minimize the stresses because you're predicting with that human counterpart where they want to go. So in a minute, we're going to take off. We didn't start running, but this just shows you over the entire map how well the performance was and how it looks like on a real carry data. And you can see we switched directions there. And we're navigating through these cluttered environments. And so the output that you saw in terms of the accuracy was based on all of the environments that we walked through. And so the next step is to then say, how can we transpose this to an actual robot? So, the parameters were selected with keeping such a robot in mind where you could actually observe the head pose, observe the torque, the twist, the surrounding environment, and hope to implement this directly. And so thinking in terms of control for that system, you have compliance in the arm. You can just keep that at a point you want and then use the base to control the pose with the notion that you have some expected position for the system and you can move the base in that way with the grasp constraint that you don't want to go more than 90 degrees so you don't mess up your arm. And then if you can use this prediction, it can actually serve as a feed-forward term for you, and then you can actually minimize those internal stresses as you carry, and you can have an intelligent system that's able to offload some of the cognitive properties that the human leader would have to do in planning for the entire system. So here's an entire pipeline based on the work that we showed. So you observe your human collaborator, you estimate the human intended pose, this is the work I just showed you, plan feasible trajectories to the estimated pose, and then given a grasp map, if you know where the human is grasping, you can determine how you should move in such a way to minimize the internal stresses on the load and be optimal as you transport. And so again, this is the work that we did here. This is planning the optimal trajectories and then attenuating along those paths. So in summary, these are the precision pouring wet lab assistant. The takeaways for here, we're capable of adapting to new containers, pouring precisely in a single attempt. Cooperatively carrying wet lab assistant is able to plan collision-free trajectories and minimize interaction forces, as well as estimate human intent. So the next step is to say, how can we take this notion of anticipating human intent and completing these complex tasks and do other really helpful things. So you can imagine helping to carry someone who's like rehabilitating. If you are able to observe them, are they in pain? Can you anticipate these things as you perform this complex task? Or maybe you're helping a disaster relief person carry a load. If they begin to do something, can you enable or amplify whatever it is that they're trying to do? So future research would be predicting human intended pose for cooperative transport, making this more robust and complete, predicting the human motion in pain and rehabilitation, and predicting human action, enabling and amplifying humans' abilities. And I love this quote. It says, the human and robot must be able to each develop high-level plans based on uncertain information, communicate intent, and decide at a low level when and how to act. So this is the work that I did in the wet lab assistant, but I think there's so many more open collaborations in areas where it will be really great to have robots work alongside us and in these dynamic environments. So here at UW, these are a list of courses in the EE department that I could easily see myself teaching and would quite enjoy. And with that, thank you very much.
All right, thanks very much, Monroe. I'd like to take any questions people have. Yeah, please.
Excuse me. So with the carrying assistant in the second part of your talk, do you see any future research about dynamic obstacles? It seemed like you're mostly assuming static ones in the research.
Yes.
And just for the benefit of the viewers at home, the question was about situations where obstacles are kind of dynamically moving in time.
Yeah, so in this work, I definitely assumed that the obstacles were, in fact, static, that we traversed around. But you could imagine easily using a similar framework for dynamic obstacles. So if you were to, so this is really good. So this actually goes to the notion of the importance of the transient analysis. So assuming the Markov process, I only have that snapshot, and I'm using that to predict on a small time horizon. If everything in my environment is moving slow enough, this might be a valid assumption as long as my time horizon is short. But the longer the time horizon gets compared to the velocity of the dynamic obstacle, such an assumption will break down, and that's a great question. So some future directions, I think, would be really considering that time as a part of it. And you can imagine even using, for instance, like a recurrent neural network that has the internal state inside that could accommodate both how the system is doing, possibly give you more information about what the human intends to do, and also possibly accommodate the changing map and give you notions of how obstacles move inside. So I think that's a great next step. Thank you for that question.
Yeah, Matt.
I'm really interested in the pouring problem. And one question I had is that sort of the mass of the source container is implicit in the model that you have, but it's not explicitly represented.
Yeah.
Do you have any data about the mass of the source container over time, and is there value in using that mass as a part of the model?
Okay.
Yeah, so I think if I can summarize, the question was about whether including the mass of the pouring container would have an effect or would maybe improve the results or something of the pouring task.
So that's a great question. So, so one consideration is it would help you in terms of the fall time, right, to know as soon as that mass changed. But what we were really, what was really challenging is as you begin to pour, that the geometry of the container plays a big role in that transient height. of the fluid, and that is independent of the weight. If you hold it still, because of the geometry of the container, that transient is going to be different based on that container geometry. So you'll still run into problems with that. However, you would eliminate the need for having to also accommodate the fall time, but you would still have to do everything else in terms of understanding what's going on inside of your container. So it could be helpful with eliminating that part, but it's still challenging for that reason.
Yeah, please.
For the pouring problem, did you consider having to break the surface tension of the liquid? For example, like different beakers and different containers have different properties. So, you know, they might be able to break the surface tension easier, or maybe they just suck at breaking the surface tension of that liquid.
Yeah. So I didn't investigate that. We made life easier on ourselves. Sorry. So he asked about the surface tension. Was that a problem and a consideration for different container geometries? So we didn't. We worked with water. We made life easier for ourselves in that regard. And I think that's a really interesting future direction. If you want to pour things where such parameters are really important, then your modeling may change. So, you know, if you wanted to fit in the same framework we did, which is not a must, but you could imagine using some software like NVIDIA Flex, where you could actually tune those properties and accommodate these weird viscous effects and surface tension that you would actually have. And so these are considerations that you could use such a platform for. The challenge with the closed form thing is, you know, again, ultimately you'll find yourself in this dynamic situation because, you know, the Navier-Stokes equations are what you would use to model such dynamics, and there's no closed form solution for that. So you're back at the stage of, you know, modeling such a thing. So, yeah. Sorry.
Yeah, please, Shinkai.
Hi. In your carrying experiment using convolutional neural network, I'm very curious. How did you define the loss function during the training? Because right now, you don't really have ground truth. You have human ground truth, but you don't really have the real robot ground truth. How much torque I need to use, what kind of speed of the movement, but you need to train that network. It's unlike autonomous driving where you have a real human driver, and eventually we want to use the human driver's steering wheel angle and the gas pedaling, brake pedaling to determine how to drive. But here, we don't really have the real robot to do the maneuvering. Then suddenly I need to change that network. How did you collect those ground truths, as well as how do you define loss function?
Yeah.
So yeah, it sounds like the question is about how to define the ground truth in the collaborative carry task, and how did you choose the loss function for training?
It's great questions. So the first is, you know, we're working in a space where there are not a lot of examples on how to do this, right? So we made the assumption that the human model would actually be the best ground truth we could get. So when I collected all of that data, I have that history on how, you know, where the human leader actually intended to go, and I assumed that the human follower was doing the best job possible. So our goal was to approach their behavior. And so that ground truth came from looking at that observed data between the two humans carrying. The loss function is an interesting story. So with that, we actually, as I was saying, predicting that future pose, we had all the data present, so we could look at that future time. So the final model just had a loss function that described the error, the final error for the predicted pose, and propagated that backward. But at one point, we did try an alternate model where, because we believed the head and a step indicated the desired position, XY position, we fed that backward and connected that directly. And we actually didn't have convergence. And the hypothesis for why that is the case is because in those scenarios, like if you're walking down a hallway, it's not always going to be a direct correlation to the expected position. And in fact, it's highly coupled with the other terms that you would see. So with the different testing of the models you could do, and obviously, you know, when designing networks, you know, there's sometimes many solutions and some that are better than others, but we found this to work quite well. If you allow those things to be coupled and associated in this way, we found that we had good results with this structure. Does that answer your question?
Yeah, okay, but what if after the training, then your neural network give you the pose, which is not a possible pose? How did you impose that constraint?
Yeah. So that's a great question. So his question was, what if the network gives me a pose that's not possible? So here's where, you know, the key is I stated it wasn't end to end. Right, so all of the other things that I mentioned in that full pipeline where you given a pose, you plan a collision-free trajectory, and then you control along that. If the suggested pose were infeasible, that lower level of control would catch that. right? So we saw that it did quite well, but if it's wrong, you don't want to have to suffer the consequences from having that end-to-end solution. So by having that hierarchy in the control, we were able to get that expected pose and still leverage the quality if we did a good prediction, and if not, we had that safety check because you can actually see if it's feasible to reach that goal. That's a great question.
Okay, great. I think we're coming to the end of our time here, so if there aren't any other questions, let's thank Monroe again, and maybe other questions can come down and be taken offline.